Okay, so today we're going to do a review for the next exam 6 on chapter 17, entropy. And I think since I don't have all these formulas memorized, I think the first thing I'm going to do is over here on the side, put the formulas that are useful to us, because they're going to be available on the exam. And let's see, first one I want to get to is well, I know this one already, so I'll put it up first. Gibbs equation. And then, okay, S total equals delta S system plus delta S surroundings. And then delta S surroundings equals minus enthalpy over temperature. Oh, no. It is K based upon pressure is equal to the K based upon concentrations times RT to the change in moles of reactants and products. There was one other. That might be it there. Let's see. Here it is. That's the, yeah. No, see here. That's a mistake. Should be in. Okay. Well, let's put it up here too. The natural log of the equilibrium constant equals H0 R times 1 over T plus delta S standard conditions over R. And actually, there's one more. Oh, it is. Okay.
On the bottom in the middle, if you run down constants on the bottom.
Okay. Maybe I've got an old copy. I bet I do. This is a key. So it's in your version. Okay. Well, that's good to know. And there's one other one. And this is similar to enthalpies that we used before. The delta S for the reaction under standard conditions equals the sum. Oops, better than that. The sum of, and we have to include the moles, of the delta S0 for the products minus the sum of the delta S for the reactants. Here we go. Okay, so let me gate these off here. Then we won't have to go looking them up. I might have to refer to my notes then. Okay. Excuse me. So this is I'm working from version 1 of the review document here. And I'm going to stop at number 9. At 1 atmosphere, liquid water is heated up above 100 degrees. So pressure equals 1 atmosphere, that's standard conditions, but the temperature is greater than 100 degrees. Doesn't say exactly what it is, but what we know from this is that this temperature is higher than the equilibrium temperature for boiling water. The delta S surroundings for this process is what? Okay, so that's the question. We're looking for the delta S of the surroundings. Okay. Let me draw a picture. You've seen this one before. This is the system. This is the surroundings. And orient myself here. Okay. We're going to use this formula right here. We know that the delta S surroundings, and I'll just remove that, is H over T. Okay. If we were at equilibrium, then the heat added, the delta S in, delta S out would be equal. We would be at equilibrium. But since the temperature is higher here, then what we've done is we've added more energy to the system. And that being said, well, actually, let's back up even before that. What type of process is this relative to the system? If we're adding heat to the system to boil that water, right, that's a positive value. Q is positive. Right? So that means delta H is also positive. So if we say that, then a negative times a positive at any temperature is negative. So the delta S for the surroundings will be negative, right? Less than 0. Okay. And that would be, of our selections, that's B. I was starting to make it more complicated than it needed to be. I'm going to leave that up there. We're not needed yet. I think 10 is the next one. Yep. Okay, now we're at 1 atmosphere. Liquid water is heated above 100 degrees. What's the delta S for the creators of these problems are equating delta S universe to delta S total. That's what we're really after. Because we know that delta S universe in an absolute definition is always greater than 0. That's the second law of thermodynamics. So we're actually interested in delta S for total. Okay, so we know that the process is endothermic. Delta S surroundings is negative. So we're looking at this one right here. System plus surrounding. We've already determined that for this process, that's a negative value. If this were at equilibrium, then delta S would be, total would be 0. And this would be the opposite sign same magnitude. But when we're adding heat to our system, then we're actually increasing this one above delta S surroundings. Okay. Let's see if that makes sense. Yeah. Since we're not balancing input and output at equilibrium, then this one is actually greater in magnitude than that one, which means, and I should specify this is in magnitude only, not in sign. Obviously, it's greater than that one because it's positive and that one's negative. But if we disregard the sign, then the absolute value of this one is greater than that one, which means that overall, that would be positive. So the delta S total for this system is positive. It's greater than 0. And that's A. Did I lose you? Okay. Sometimes I lose myself. So when I'm working these problems, when I'm in the background, I'm actually trying to convince myself. Because I can't convince myself, I shouldn't be expected to convince my students. Okay. This one looks massive, but it's really just a series of statements that we want to see which one is true. All right. So let's see what these have in common. By spontaneous. Okay. A through D, they all say by spontaneous, we mean something. All right. Let's see. And E is none of these. None of them are true. Oh, excuse me. By spontaneous, we mean that the reaction or process will always proceed to the right as written, even if very slowly. Okay, now, yeah, that's true. The first part of that statement is true. Okay. Let's see what the second part says. See, I need to read it up there because I got something in the way here. Increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. We know that if you increase the temperature, you're going to affect the value of delta S. Let's see, 11. Yep. And that I know that's a false statement, but I need to justify it. Right. And here's where I would go to this equation right here. Okay. We know that this has to be negative in order for the reaction to be spontaneous. We don't know what this is. We're not told what it is. But what does the temperature have to do with it? Increasing the temperature may speed up the reaction. Yeah, it's possible. But it does not affect the spontaneity. If we change the temperature here, it's going to change this whole calculation. And that will affect delta G. It could make it more negative. It could make it positive and change the spontaneity. Right. So simply based upon that equation, if we mess with the temperature, we're going to mess with the spontaneity of the equation. So that makes this part false. Okay. How about B? The first part of the statement is the same. Second part of the statement says increasing the temperature may speed up the reaction. Oh, wait a minute. Are those the same? Oh, no. Reaction or process will always proceed to no. Right. The first one said to the right as written, which is true. And the second one says to the left as written, which is false. Spontaneous, we mean that the reaction or process will always proceed to the right as written, even if very slowly. When we write an equation and we say it's spontaneous, then as written, right, reactants to products, we're saying that that's spontaneous as written, unless we specify differently. We have to assume that that's true. That makes this part true. And this one saying spontaneous to the left as written means it's false. So we don't have to deal with the rest of it. So let's look at C. By spontaneous, we mean the reaction process will always proceed to the left as written. Okay, so that was false. It's like this one, and it's false in the first statement. So D says, reaction process will always proceed to the right as written, if very slowly. Okay, we're true again on the first part of that statement. How about the second part? Increasing the temperature may speed up the reaction, and it generally affects the spontaneity. That is true, based upon this argument. So both parts of that statement are true for D, and only D. Stop me if I lose you, okay? Let's see, I'm gonna skip a few here. There's a lot of redundancy built in. I think we get down into the 30s first, or we see another highlighted one. There we go. Okay. 34. Let's see. So the clean slate here. The following reaction: carbon dioxide plus water. Carbon dioxide plus 2 water. Gas also. Yep. Gas. Yields methane plus carbon monoxide, I bet. Nope, oxygen. Sorry. Missed my guess. And delta H, I'm gonna write it up here out of the way, is given as 803 kilojoules for that equation. Let's see. Yeah, this is an endothermic reaction because that value is positive. And now what's the question? Which of the following will increase K? We're looking for the effect that will increase K. All right, I gave you 2 ways to solve this problem. One was using a plot of this equation, where we plot 1 over temperature versus natural log of K. And that works, but if you're in the middle of a test, you might want to work a little quicker. So the second approach is to place this term in the equation where it's where we can use Le Chatelier. That being a positive value means it's endothermic. That means that one has to be over here, 800. That. Okay. Now, how would we increase K? Well, what is K? K is equal to methane and oxygen squared over CO2 and water squared. So how do we get that one to be bigger? Well, we increase the numerator and decrease the denominator. So increasing the numerator would be trying to force the reaction to this side. So how would we do that with our selections? Let's see, we need to be A, B, and C. The others are combinations of those. Decrease the number of moles of methane. If we decrease the moles of methane, well, okay. What factor is the only one that we've studied that will change the equilibrium constant? Temperature, right. So when we change the moles, that has no effect on the K. It changes the equilibrium position, of course, but it doesn't change K. Volume B, C, increase the temperature. So let's see, increasing the temperature would do what? It would add to this side, drive the reaction to the right. That would do what we want. So if we said the other thing, decrease temperature, then that would be false also. And we'd have to say none of the above. So, hint, hint. Just in case I get sneaky. Oh, this was 34. Okay, I think that's a little easier than working with this equation. Either way it works. Because this one has a temperature change involved and its relationship to K. Okay. Let's see, 36 is next. All right. We have a gas phase reaction, nitrogen monoxide and 1/2 O2. Nitrogen monoxide. It says it's gas phase, so that's why we didn't write gas into the equation, because every one of these reactants and products is a gas phase reaction. And the delta H0 for this reaction is a negative 56.91 kilojoules. Wrapped around to the next line. And the K is given as 1.46. I'm not sure if we need all this information at 25 degrees C. Okay, now that's everything that's given. What would be the effect on the amount of NO present? What effect would be on the amount of that present if we did what? Compress the system to a smaller volume. Keep the temperature constant, right? So the K is going to stay the same, and we're compressing. So we're decreasing the volume and increasing the concentration by doing that. Okay. And that has an effect on the entire reaction. So what would be the effect on this? So remember with the Le Chatelier, all we need to know for a change in volume, which affects the pressure. Yeah, I should put pressure here. We increase the pressure. Is the number of moles of gas on either side. So on this side, we have 1.5 mole. On this side, we only have 1 mole. So if we increase the pressure, we're going to drive the reaction to the smaller mole side. So we're going to decrease the concentration of NO with that process. And that would be B. Okay. The answer does not depend on the value of K because we didn't change the temperature. All right. Let's see who's next. Let me skip a few. I think we pick up duplicates of those in the next version. 46. Okay. So we're looking at following data, calculate the normal boiling point for formic acid. So formic acid is this. And the boiling point would say we're going to gas. Okay. And that means that we're at an equilibrium situation. So what that means is if we have our system surroundings, that is whatever change of entropy and enthalpy to surroundings is the opposite to the system. Okay, so we know that, let's see, what else are we given? We're given enthalpies of formation and entropies for each of these. So we know our formula here says delta S surroundings equals minus delta H over T. But we're interested in what's happening in the system. So that means the delta S for the system equals positive delta H over T. And the normal boiling point would be found in that term right there. So what we need is to calculate the delta H for that system and the delta S for the system. And we can do that from the information given. And so the delta H for the system would be product minus reactant. So that would be, let's see, product is in the gas phase minus 363 minus a minus 410. And that's kilojoules? Yeah, kilojoules. Okay, so let's see, what's that value? Get my calculator out. Unless you guys got yours out and you beat me to it. Let's see. 410, that's positive then, and 363 minus. So that's plus 47 kilojoules. Okay. Delta S for the system equals what? Notice this is in joules, not kilojoules. So we gotta watch out for that when we do our calculation here. Let's see. 251.1 joule minus 130. Let's see, does that make any sense? Yeah. This is for the liquid and this is for the gas. So the delta S for the liquid should be lower then. Yeah, that makes sense. Okay, so let's see what that value is. 251.1 and 130. So this is 121.1 joules. And this one is that's 1,000 times. So it's 4.7 times 10 to the 4th joules. Okay. So now we can look at this system. Let's solve it for T. Bring T over here and put that one over there. So delta H over delta S. Right. Delta H is 4.7 times 10 to the 4th. And delta S, actually this is joules per K. All right. Because we canceled out the moles when we did this calculation here. And delta S is 121.1. So the joules cancel, leaves us with K. Let's see. This one needs to be times 1,000. And I can flip it and divide again. Okay, this is 388.1 K. And is the temperature? Yeah, it's in C. So minus 273 is 115 degrees C. That would be E. Okay. That wasn't too bad. All right, 52. Calculate the delta G for water plus oxygen yields hydrogen peroxide at 600 K using the following data. Okay. See if there's a trick to this one. Oh, we have Ks. So if we're going to calculate the delta G, what's the relationship of Ks and delta Gs? We might have. Okay. There's your delta G. Oh, yeah, if we use maybe we're missing a formula. Yes, that's one I didn't put up there. Which is, what was it again? Delta G log K. Okay. And what? Oh, that's right. That's equilibrium. Okay. And I have to assume that this K is in terms of concentration. Oh, 52. I was looking at the wrong one. Okay. Oh, maybe it doesn't matter. We've got to find out the value of K first. Because we have temperature. All right, so we're going from water plus 1/2. Oops. Oh, I'm there. O2, 1/2 O2 gas is in equilibrium with hydrogen peroxide. Right? At 600. Okay. So it's elevated temperature. All right. So first of all, we have to combine those two equations to get an expression for K for this expression. So the first one is H2 plus O2, which puts it on the correct side, yields H2O2. Okay. Oh, this is gas also. Okay, so what's the K for this one? Equals 2.3 times 10 to the 6th, and they're nice, they gave us the K at the right temperature. Okay, the second one, we don't have any water on this side. So we're gonna have to flip the equation and divide by 2, right? So that would be 2H2O yields 2H2, I'm gonna put it up like this first, plus O2. And we have to take this one and divide by 2, because we only need one of these. Actually, we only need half of that one also. Oh, maybe it. No, we don't. Because this is going to take care of it. Okay. But the KP for this side is 1.8 times 10 to the 37th. So what do you do when you divide by, or when you multiply by any factor? What does it do to the K? That factor becomes the power. So the new K is actually going to be inverted and divided by 2. Excuse me, inverted should be a power to the 1/2. Wait a minute. No, that's 37. We flip the equation, so that means the KP for the flip should be negative, right? We had to invert the equation. So the KP for this one in the first place is inverted. Okay, but now we multiplied it by 1/2. So that means it has to be to the 1/2 power. Right. So this is -1 to the 1/2 power. All right. So what is that? Let's do this in steps. What did inverting it do? The KP to the inverted. Right. So that would be 1 over 1.8 times 10 to the -37. Correct? I think that's the way that goes. Was it 37? Yeah. Yeah. So let's resolve this one first. So what's the inverse of 1.8? I'll tell you what, let's just take the inverse of the whole thing. Like this. 1.8 exponent 37 and just invert it. There we go. 5.56 times 10 to the -38. There we go. That's KP inverted. And then we have to take that to the 1/2 power. So KP to the 1/2 power is actually the square root of that value. So I just hit my square root key and I get 2.36 times 10 to the -19. So that's the K for this expression once we apply this. So when we apply that, that makes this one 1, makes this one 1, makes this one 1/2. Okay. So now we can add them together. We bring this one down. Right? That one. And then 1 on this side and 1/2 on that side reduces this one to 1/2 O2. Okay, and then now we have, see, we took care of that one. And that one cancels here and here. And we took care of this one, and then it left us with hydrogen peroxide. Okay. So we've got this value for that modified one. And we got this one for the top one. So what do we do to get the K for this reaction? We multiply them. Right? So I still got that one in my calculator. I'm going to multiply it by 2.3 to the 6th. And that gives me 5.42 times 10 to the minus 13. Okay, so that's the K for our reaction. See if I'm on track. Yeah. So if we go now to this equation, that should be 0. Delta G0 equals minus, what's R? 8.3145 joules per mole K. And then temperature is given in K. That's nice. So our K's cancel. And then the log of our K. 5.42 times 10 to the minus. Okay. So I got that one already in here. I'm going to take the log of it. Natural log. Natural log. And then 600.1 times that. And then 8.3145. Change that sign. Times. I get 1.41 times 10 to the 5th. And free energy should be what? Joules per mole. Is our answer in joules? No, it's in kilojoules. Okay. So if we take 1,000 out of this one, that leaves us with 10 squared, 1.41, and that's kilojoules per mole. Or if it's in standard notation, it'd be 141. Okay. Oh, that's a lot of work. It calls upon your memory of how to combine equations from Hess's law. Actually, Hess's law references only enthalpies, but we used it for equilibrium calculations too. 53. Okay. Consider the reaction 2NO2 yields N2O4. N2O4. And what are we given? Delta H is minus 56.8. Delta H0 equals minus 56.8 kilojoules. And it's given us delta S also. Yeah. Delta S is minus 175 joules per K. Does that make sense? Under standard conditions? Yeah. Delta S for the system is decreasing from 2 to 1. That makes sense. So in a container at 298 K, which is standard conditions, 298 is 25 degrees C. So these are standard conditions, and that's what we're indicating here. So we're good. Mixed an initial partial pressure of 2.4 atmospheres for what? Which one's first? N2O4 is 2.4 atmospheres. That's tricky. Give us the data backwards, 0.42. That's our starting conditions. Which of the following statements is correct? Well, what are they saying? Some N2O4 will decompose, or NO2 will dimerize. The system is at equilibrium. The final total pressure must be known to answer this question. Okay. So we're looking at which direction is it moving. All right. In order to do that, we need to answer the question. Remember, when we're given absolute amounts of our reactants and products, we can't that's initial amounts. We can't calculate K because we're not at equilibrium, but we can calculate Q. So Q would be N2O4, and this would actually be partial pressure. And then partial pressure of NO2 squared. So if we do Q and we can compare it to K, we have to calculate K now. Right? So we can compare and see which way it moves. So in order to calculate K, we need that previous equation, delta G0 down here, this one right here. So we need to be able to resolve this equation, minus RT log K. All right, so how do we get to K? Well, actually, we need more than that. Yeah, we need more than that because this only has K in it and delta G. We don't have delta G yet, but perhaps we can find delta G from this one because we do have delta H. We have the temperature and we have S. So now you have two approaches. You need to find this one in order to get that one. But to get this one, you need these two. So you can calculate this one separately, get a delta G, plug it into this equation and find K. Then you can calculate Q and compare it to K. Let's go ahead and do Q while we're here. So Q would be N2O4 divided by, let's see, 0.42 squared. So we'll get that value. This is the non-equilibrium situation, 0.42 and then squared. Let's see, where's my square? Here it is. Right. So this is 13.6 is Q. The way I solved it in work problems is I combined these two, so I don't have to do one calculation. So if we set, this is delta G0 and this is delta G0, we can say minus RT log K equals delta H0 minus T delta S. Because they're both equal to delta G. And then what we need is K. So we got to put this term on that side. Delta H0 minus T delta S0 over minus RT. That'll give us log K, and then we just take the anti-log and we're good to go. All right, so we plug in the values that we know, and these have to be in terms of joules. So this is going to be minus 5.68 times 10 to the 4th joules. That's one of the tricks to this calculation. Minus 5.68 times 10 to the 4th minus temperature, standard temperature, 298. 298K times delta S, which is minus 175. And then minus R, 8.3145 times T, which is again 298K. There we go. So this should give us the natural log of K. Let's see. 5.68 sine exponent 4. And then I'm going to go 298 and 175, change that sign times. I change the sign again because of this negative out here. And times this value, which gives us a negative on the top. Okay. So this term right here, in case we get messed up, is minus 2.96 times 10 to the 9. And this one is 8.3145 negative times 298. And this term is negative 2.48 times 10 to the 3rd. So I divide that one into this one, that should give us a positive value. Let's see if I got it right. Yep. So this is 1.196 times 10 to the 6th. And how do we find K from that? This is the power of E that gives us that number. So it's E to that power. The anti-log is E to that power. It's like our pH exercises. So I just need to find E to the X in here. There it is. Oops. What did I do wrong? Gave me an error message. Okay, I did something wrong with the calculation, I think. Because it's not giving me. Okay, that one, yes. 298K, 175, yes. Okay, that's my error. That's the wrong value. You guys will be checking me on this. Unless you're too busy taking notes. So let me plug it in again. 5.56 exponent 4 and 298 75 times, and then that's that was my problem. I multiplied this. So that should be there we go. This is negative 3.45 times 10 to the 3rd. Now you're talking. Then 2.48 3. So this is wrong. And it should be 1.391. So now I can take E to the X. And that's 4.02 is K. All right, now we can say Q is greater than K equal to 4.02. So if Q is greater than K, which way is it moving? Right, if Q is greater than K, that means we have too much product, right? So it has to move back to the other side. That means that any of this, well, some of this will decompose into NO2. And that is A. Right? I'm going to shift back to the left. based upon that calculation. Just don't make my mistakes. My key was made a long time ago. That's why useful information is not up to date. 56. Yeah, 56. Okay. Oh, I forgot to mark. Oh, there's- Go. Let's see, following system at 25 degrees. PCl3 gas plus Cl2 gas, I think. Yeah, we're going to PCl5. PCl5 gas. And delta H, standard conditions is minus 92.5 kilojoules. Okay. If the temperature of the system is raised, the ratio of partial pressures of PCl5 to the partial pressure of PCl3. Oh, this is simple. What type of reaction is this? Exothermic. That means that term has to be on this side. Okay. So if we raise the temperature, we're going to drive the reaction back this way. So now the ratio of partial pressures PCl5 to PCl3 should do what? This should decrease, that should increase. This ratio should decrease. Because we're making that one smaller and this one bigger. Okay. I like that kind of problem. Simple, simple, simple. Okay. Let's see. Okay, it looks like I got myself a note in here. It looks like version 2, number 56 is based upon the same scenario as 58. So we're going to do 58 and then we're going to jump to 56 in version 2. Starting to get weak, isn't it? The equilibrium constant in atmospheres for the dissociation reaction Cl2 yields 2Cl. Cl2 gas. And going to 2Cl. Yes. Okay. Was measured as a function of temperature in K. A graph of log K versus 1/T for this reaction gives a straight line slope. Okay. This actually, what are we doing here? This is bond energy. The amount of energy it takes to break that bond and give you in separate atoms. Okay. So we're measuring bond energy at different temperatures. Well, actually, we're not measuring bond energy. We're measuring the K. But that's the reaction that's expressed here. Okay, so if we draw this as a log K versus 1/T, right? We change the temperature. The response is log K. We get a straight line with a slope of minus, so it's a negative line here with a slope of minus 1.651. Slope minus 1.651 times 10 to the fourth. And an intercept up here of 14.51. 14.51. Okay. All right, we know we're talking about this equation right here. Log K equals minus delta H over R 1 over T plus delta S 0 over R. So that slope is equal to minus delta H over R. Right? And the intercept is equal to delta S over R. Okay. What's the question? Which of the following statements is true? Oh, okay. Well, let's see. Let's take them one at a time. A, B, C, D, and E, none of these. So the first one says reaction is exothermic. Is that true? Well, let's see. In order to be exothermic, delta H must be negative, right? If delta H is negative, then that value would be positive. Right? So that's false. This is actually endothermic. Okay. The reaction is, oh, well, there you go. Endothermic. That one is true. And we don't have any, the reaction rate is high. We can't tell from that, not from that plot, anything about the reaction rate. Because, well, we could go into particulars, but overall, what are we studying? We're studying entropy, free energy, spontaneity. Those are equilibrium discussions. We're not talking about kinetics at all. It could get there fast, it could get there slow. Or we could go in and use our energy of activation equation. You know, maybe get some information from that. But what we're given here, no. We can't say anything about the reaction rate. The reaction is not spontaneous. Well, is the reaction spontaneous? Well, this is the delta S for the system. Spontaneous would be delta G minus T delta S. Let's see, maybe we can figure that one out. This is zero. Okay, how about delta S? What sign is it going to be? Well, this is positive, so that one has to be positive. Okay. And the temperature is 298. Okay, so that's positive. Delta H would be that value. Well, it's also positive, right? Yeah, that one's positive. So if this is positive and this is negative, we need to know, is this one bigger than that one? Right, can we tell that? Probably. Right. So if we say, what would be delta, actual value for delta H? Delta H, 0. Let's do it this way. Negative first, and then we can put the R on this side times a minus 1651 times 10 to the fourth. And then we change the sign, just put the sign over there like that. And this is 8.3145. Well, we can do that calculation. Let's see. 1.651 exponent 4. And overall, it's going to be a positive, so I'm not even bother changing the sign. 8.3145. This is 1.37 times 10 to the 5th. And that's joules. So kilojoules will be 1 point, let's see, no, it needs to be joules. Because we're gonna put it in this calculation, it has to stay joules. Okay, so then T, what's delta S? Well, delta S 0 is 14.51 times 8.3145. Sure. 8.3145. So that's 1.206 times 10 squared. So we can plug that into our equation. Delta G0 then is delta H, which is positive 1.37 times 10 to the fifth. Minus 298 times delta S, which is 1.26, 206, excuse me. Just let's see, times 10 squared. Did I put those right? Yes. Okay. So let's see, is delta G positive or negative? Well, 1.206 times 298 gives me a negative 3.59, actually rounded off, 60 times 10 to the fourth, and 1.37 times 10 to the fifth. All right. So delta G is positive. 10 to the fourth, 10 to the fifth. So delta G is positive. That reaction is not spontaneous. You know, well, D is right also. Uh-oh. I need another selection in there. 2 of the above. Okay. That's my problem, not your problem. So you could put either one and be right. You could put B or you could put D. After doing that calculation, I didn't think that far ahead. Should have done the calculation. Why would we? Okay, let me see what the work problem says. 58. Maybe it's already solved. No, it doesn't bother. Just says endothermic. But we found that it's non-spontaneous because delta G0 is positive. That was also true. Not spontaneous. Did I put the right temperature in there? Oh, a function of temperature. All right. Technically speaking, we can't say. We can't say the reaction is not spontaneous because there's several temperatures on here. Right. Which temperature is the right one? If we're at standard conditions, it's not spontaneous. So if we said the reaction is not spontaneous under standard conditions, that would be right. Okay, so that's my out. We can't say the reaction is not spontaneous because we don't have a temperature to work from. Okay. Fancy footwork. Oh, yeah. So we're going to 56 version. Yeah, version 2, 56. All right. Why erase all of it? So let's scroll down to 56. Thanks for reminding me. So I didn't erase all of it ahead of time. Okay, so we've calculated this one in terms of joules. We just take 1,000 out of that. And that gives us 1.37 times 10 squared kilojoules, or move the decimal place, 137. Close enough. 137.3. Okay. So let's see. Do I have any more highlighted in version 1? Let's see. Go back up version 1. Yeah, I do have 59. We're going to go down to 59 now. Version 1, 59. Okay, for a certain process at 300K. Oh, don't make this one too complicated. Temperature is 300. Okay. Delta G is minus 10.4 kilojoules. This is everything we know about this reaction. And delta H is minus 7 kilojoules. Okay. If the process is carried out reversibly, the amount of useful work that can be performed. Okay. Which one of these terms, if any, refers to useful work? Gives free energy. Right? So if this is negative, it's spontaneous, so we can get useful work out of the process from left to right if we knew the reaction. So this one references useful work, the maximum amount of work that's possible to get out of there. All right, so the value for W is minus 10.4 kilojoules. And we say minus because that indicates that the useful work we're getting is leaving the system. We're extracting work from the system. Remember when we put system here and surroundings, then everything that goes in is positive and everything that goes out is negative. And just fill in whether it's Q, whether it's delta S, whether it's delta H, whether it's work, they're all that same sign convention. So that means we're extracting, we have the potential for a reversible process to get that much work out. Of course, you never do, because all processes are irreversible. That's a theoretical world, but we start with the theoretical and then we apply reality to it, and that's where we end up. Let's see. Oh, we're into version 2 now. Okay. Version 2. There. And let's see. Question number 2. 2-bulb flask contains 5 particles. What's the probability of finding 5 particles on the left side? So we have 2 bulbs here, and we have an A, B, C, D, and E particles. What's the probability of finding them all on that side? There are 2 ways to do this. You can work out each of the possibilities, right? What's the probability of finding 1 on this side? Right? I think that's the way I approached it. Yeah. We take 1 particle at a time. What's the probability of finding A on this side? And we just ignore the rest of it. The probability of finding A on this side is 1 out of 2, 1/2. What's the probability of finding, say, B on either side? It's also 1/2. And we can go right down the line. For C, and for D, and for E. So in math, when we say we're combining probabilities for each of these processes, you multiply the probabilities. So that's 2 to the 5th, or 1 over 32. So whatever that happens to be in percent value. 32 invert 3.125. 3.125% is the probability of finding all of them on this side. Okay. Have you done did y'all do probabilities in any of your math classes? No. Not even algebra? Oh, statistics? You're gonna take statistics? No? Oh, okay. Well, memorize it. That's a fact, right? We just look at the probabilities for either side for each one, right, separately. And then since we're all moving them on this side, then it's the product of each of their probabilities. Now, if we let some of them be on one side and some on the other, that complicates things. So I'm not going to throw that one at you. Actually, we could do Pascal's triangle. That would be easier. If we had a mixture, we could do Pascal's triangle. But I think I left that one out because it's kind of a complicated also. You have to set it up first before you can use it. You know what a Pascal triangle is? Okay, if you start at 1 at the top, and then you say 1 over here, then 1 plus 1, let's see, you have 1s on the outside, and 1 plus 1 is 2, 1 plus 1 is 2, 1 plus 1 is 2. Is that right? Or is it 2? I went too far. 2, 1, there we go. Is that right? No, I'm sorry. It's take these two. You have 1s on the outside, and you take these two added together is 2. Then you have 1s on the outside. These two together 3, these two together 3, and 1. And then you keep going like this. 1 plus 3 is 4, 3 plus 3 is 6, and it's 4. So that's the progression for Pascal's triangle. Pascal was, well, you remember his name from pressure, gas pressure. He was a polymath. He did lots of stuff, which was typical in those days because there wasn't as much to remember. You could dip your toes in lots of different pools. Nowadays, you spend your entire life working on one little corner of science. Okay, so let's see. We answered that one. Let's go down to who's next. 14. I want to give another marker. This thing's pooping out on me. That's what I get for buying cheap. 14. Go. For the process, let's see, what is this? CHCl3. Trichloromethane. There's another name for it. Solid. And we're going to liquid. And the delta H for this process at under standard conditions is 9.19 kilojoules per mole. And the delta S for this process is 43.9 joules per mole. Hey, what's the melting point of chloroform? There it is right there. So we're looking at this one here only for the system. So at equilibrium, we would say that the delta S for the system, since we're at equilibrium, is a positive delta H over T. And that T is the equilibrium temperature, which in this case is the melting point. So what we need to find out is, and this, remember, if this has no subscript, that's system. And so we have, we solve for T, bring the T over here, delta H, delta S, and we have to reconcile the units of measure. This one would be 9.19 times 10 to the third joules, not kilo, joules per mole. And this would be 43.9 joules per K mole, which cancel the joules, cancel the moles, and leaves us with K. 9.19, exponent 3, and 43.9. Yep, divide. So this is 209.3 K, temperatures in C, of course, minus 273. So it's going to be a negative degrees Celsius. Minus 63.7 degrees C. Or 64 degrees, rounded off. So minus 64 degrees is when this process happens. That makes sense. The room temperature chloroform is a liquid. I used to use, remember what chloroform used to be used for? It was a surgical anesthetic, right? They put you under with chloroform. Now this little mask, and the anesthesiologist would sit there and drip, drip, so you continuously breathe that stuff. That was before they had intubation or gas mask for the patients. Now they do it all as gases. Well, they don't do it all as gases. They give Versed to relax you first, right? And then they hit you with the gaseous anesthetics. Yeah, better know what you're doing, right? Or you end up like Michael Jackson. Let's see, who's next? 20. True. What's the one coming across our border now? I forget the drug. They're putting it in heroin and cocaine, killing people with it. Fentanyl. You hear in the popular media, they'll say fentanyl. Now that's a real compound, but that's not the one that's coming across our border. It's fentanyl. That's the one that's coming across the border. And that's the surgical anesthetic. That's a painkiller. It's extremely powerful too. Thousands of times more powerful than morphine. Okay, number 20. In which case must a reaction be spontaneous at all temperatures? Okay, in this one, I don't even need to look. Get a reminder for this one. In which case must a reaction be spontaneous? If we're looking at delta H's and delta S's, then we're looking at delta G equals delta H minus T delta S. So under what conditions is it spontaneous at all temperatures? If this has to be negative, then this term should be negative. That means that has to be positive. This has to be negative. If that's the case, if system entropy is positive and it's exothermic reaction, it will be spontaneous at any temperature. Right, because this term now becomes negative, plus negative. It's a negative there. So D, delta H is negative and delta S is positive. Yep. That gives you spontaneity at any temperature. Okay, 26. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs of delta H, delta S, and delta G? A stable diatomic molecule, stable diatomic, X, 2. And I'm sure we're talking about gas. That forms spontaneously from its atoms. So we have 2 atoms here. And it says it's spontaneous, right? So if we're looking at delta H, delta S, and delta G, if it's spontaneous, we know that one has to be negative. Okay, so it's either B or E. What else do we know? Well, if we're going from 2 to 1, then this one is also decreasing. When we use our simplified version of disorder, it's becoming, oh, excuse me, more ordered. No. I was right the first time. Maybe more ordered is negative. And delta H, we know that when 2 atoms come together and form a bond, that they give off energy. They release energy. So that means this is exothermic. They're all negative. Let's see, is that the way I explained it in here? Let me check. It's been so long since I wrote this thing out. I wonder if I'm making sense again. Yeah, that's good. Right, scroll. Let's see. Here we go, 31. Calculate solubility product for salt at 25 degrees. Okay. If we're looking at KSP, the solubility product, we start with the solid, right? And it yields aqueous and aqueous. Okay. So the K for this one would be, let's see, which one of these are we using? What are we given? Oh, we're given delta G's. The delta G of formation. Okay, so we're looking at this one right here to find out what the K is. Okay. So KSP, let's see, rather than do that in my head, let's work it out on the board. Delta G0 equals minus RT log K, in this case SP. So we want log K SP equals delta G0 divided by negative RT. So we need delta G for that process. And delta G for a formation, the delta G of formation, we can use delta G formation equals the sum of products. Delta G formation for the products minus the sum of the delta G's for the reactants. Okay. So we're looking at this one is equal to what's sodium? Sodium is minus 262 kilojoules. 262 kilojoules. And we're going to add a minus for the chlorine, minus 131. And then subtract for sodium chloride, minus 383.8. These are all kilojoules. All right. So this is minus 262 and 131. This term right here is minus 393 kilojoules. And this term would be plus 383.8. 38 plus. That's minus 92 kilojoules. Okay. That needs to be in joules because our R is in joules per mole K. So this would be minus 92 times 10 to the third joules, or minus 9.2 times 10 to the fourth. So now we can get log KSP equals minus 9.2 times 10 to the fourth joules divided by 8.3145 joules per mole K. And then the temperature, standard conditions, yeah, 298. Okay, so I need to multiply this. Yeah. Yeah, that's right. And then 8.3145 divided and 298. That gives me a negative. Wonder how that's going to work. 3.713 times 10 to the 1. That's log K. So KSP is actually E to the minus 37.13. Let's see if that works. Well, that's 7.49 times 10 to the minus 17. Nope. What did I do wrong? Yeah, I should have looked at my cheat sheet to begin with. .2 kilojoules. Oh, that's the problem. I put the decimal in the wrong place. 9.2 kilojoules. So 9.2 here. This is 3. This is 3. Right? Yeah, this is the decimal place. It's a minus times a minus. That's a plus. I wonder. But that's still not the right. This should be that. 3.713. So 3.73, and there I go. That's 41 equals 41. Solubility product is 41. Okay. Math trips me up every time. Everybody follow my mistake? Okay. The other way that problem can work is if you happen to calculate the delta G for that reaction, you can back figure it to the K. So you don't have to determine the K, or you can determine the K and then you can figure the delta G. You can go either direction. 34. Check myself before I step in another puddle. Okay, 34. Gas phase reaction, NO plus 1/2 O2. Wait a minute, we didn't already do this one, did we? No. NO gas plus 1/2. We used the same equation in a previous example, but I think it was a different question. Okay, delta H standard conditions is minus 56.91 kilojoules, and K equals 1.46 times 10 to the 6th at 25 degrees C. Okay, for this system at equilibrium, how will raising the temperature affect the amount of NO present? Oh, okay. So this is exothermic, which means delta H is on this side. Okay. So how will raising the temperature affect the amount of NO present? If we increase the temperature, it's going to drive back this way and NO will increase. Just like that. Okay, number 40. This looks like a memory problem. The second law of thermodynamics states what? Well, let's do them in order, right? First law is change in energy of the universe equals 0. Second law says change in enthalpy for the universe is always greater than 0. So which one of these fits that? First one, energy is conserved in a spontaneous process. No, we're talking about entropy. Entropy of the universe increases during a spontaneous process. Yes. And we have to be careful here. That's true. The entropy of the universe increases always. But for a spontaneous process, the total entropy for the system plus the surroundings in our isolated universe would increase. Because we can decrease the combination of system and surroundings if it's isolated from the universe. The whole overall can decrease, in which case it's not spontaneous. Okay, so there's a semantic problem there. 42. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light from a burning magnesium strip. Then the following reaction occurs very quickly, very rapidly. So let's see, we have hydrogen and chlorine. Hydrogen and chlorine reacts to produce what? Does it say? It doesn't say. Oh, the equation's there, duh. There we go. Delta G is minus 45.54 kilojoules. Delta H is minus 44.12 kilojoules. And delta S equals minus 4.76 joules per K. Okay, what this tells us is, it doesn't use the superscript 0. So under whatever conditions we're talking about, whatever temperature, and temperature we're not given. Under these conditions, the reaction is spontaneous. And it's exothermic. And the entropy decreases. Now, we can't reconcile that from here. We have 2, and here we have 2. So we can't reconcile that this value from order disorder or positional entropy. So it must be energy entropy, and we've been given that. So the entropy decreases under these conditions. All right. That being said, which of the following statements is true? Well, let's look at the answers. The reactants are thermodynamically more stable than the products. The reaction occurs very rapidly. So once you have ultraviolet radiation supplying the activation energy, right, then you get a rapid rate of reaction. So the reactants are thermodynamically more stable than the products. Is that true? Well, yes, because it's spontaneous. That means that these must be more stable than those. If it's spontaneous, then that is implied from this value. Thermodynamically more stable than the products. Actually, no. Because when they're sitting there, there's no reaction. Okay, I take that back. If they're just sitting there, we haven't reached the activation energy, then these are more stable than the products. Otherwise, they would react once in contact. Right? Right, so this one's false. Then the reactants are more thermodynamically stable. The reaction has a small equilibrium constant. Oh, well, okay, how do we deal with that? Here. If we take this one, minus 45.54 times 10 to the third. And then divide by minus 8.3145 for R and temperature under standard conditions would be 298. Right. So actually we really can't tell because we're not given a temperature, are we? Exposed to. No, we're not given a temperature. So we really can't tell. But if it's at standard conditions, then the K will tell us the size of the equilibrium constant. So 45.54, 8.3, and 8.3145, 298. So this would be log K equals 18.38, and K equals here 9.6 times 10 to the 7th. K is extremely large. So if we're talking about standard conditions, then no, B can't be true. Or we can infer from the fact that once the activation energy is met, then the reaction proceeds essentially to completion, which means a very large K. Okay, how about C? Ultraviolet light raises the temperature of the system and makes the reaction more favorable. The ultraviolet light is supplied through the walls of the container. We have to assume that. The ultraviolet light from a burning magnesium strip. We can't burn the magnesium strip in the vessel, right? Because there's no oxygen. So that has to be supplied through a window, right? And that doesn't change the temperature at all. How about D? The negative value of delta S slows down the reaction. The negative delta, well, no, right? Before we said all of these values are referenced to equilibrium. Doesn't say anything about the speed of the reaction. So the negative delta S has no bearing on the kinetics. Okay, so D is false. Well, that leaves E. Is E true? Reaction is spontaneous, yes. But the reactants are kinetically stable. That's true. They're going to sit there until you reach their equilibrium, their activation energy. So what we're saying is we've got a situation where we're like this. So we got to meet that activation energy in here in order to get them going. They're stable sitting right there. Once we supply that burning magnesium strip here, then and they go down here like this. So that difference is very large, delta H. And the delta G also says spontaneous too. So they're kinetically stable for the time being, but the reaction is spontaneous. That was kind of tricky. All right. Let me skip a few and see. About this one, 52. All right. Maybe I'm going to sketch it out. All right. This is log K, and this is 1 over T. And we're referencing this equation right here. And this one is, let's see, 1, 2, 3, 4, 5. The y-intercept is at 3. Right? And then it goes down to 0.2. So we have 0.1 and 0.2. Goes down like this. There. Okay. So the equilibrium constant of a certain reaction was measured at various temperatures to give the plot below. What is the delta S for the reaction in joules per mole K? So the delta S references this value right here. This is equal to delta S0 over R. Right? That's equal to 3. So if we want delta S0 equals 3 times R, 8.3145. Oh, it's in the neighborhood of 5. No, it's a neighborhood of 25, excuse me. 24.9 joules per mole. Okay. Rounded off 25. Okay. So if I ask another question, say, what is delta H? Then we'd have to calculate the slope. So what would be the slope? Rise over run. So the rise is final 0. Excuse me. 0 minus 3 would be rise, and then run would be 0.2. So that would be -3 over 0.2. Would be, let's see, what's 2 into 3? 1.5. 0.15. That. And that would be equal to negative delta H over R. So we just multiply this times 8.315 and we get our, and change the sign, delta H would be positive. So for that other question, that's not part of this one, of course, you would have to calculate the slope before you could do that calculation. This one, you just read off the graph. Okay, let's see. Is this the one we did before? Yeah, so we'll go to 57 now. Okay. For a certain process at 300 K, delta G is some value, delta H is some value. If the process is carried out so that no useful work is performed, delta G is what? Well, delta G is the same whether you get work out of it or not, right? That's a trick question. So delta G doesn't change. If we get work out of it, then you can calculate the work. But delta G, W equals 0 because we got no useful work out of it. But delta G is still minus 12.2 kilojoules. Okay. Yeah, it was a trick question. 57. Oh, that's it. Okay. Oh, there it is. So my hard copy is deficient. This copy is fine. Any questions?